So the next big idea is matrix multiplication. Now this is important, and you're going to see an example today that actually will make it seem more relevant to your everyday life, especially if you're going to be any kind of researcher, because matrices are a great way to organize and manipulate data. But before we do any of that, I have to describe to you how we actually multiply two matrices together. So this is the second kind of multiplication that we talked about. Let's start with multiplying what I would call a row matrix. So do you guys see why we call this a row matrix? What's the order of A? A is the matrix 2, 3, 4 going across. What's the order of this thing? Okay, number of rows by columns. I see one row, right, going across by how many columns? There's 3 columns, each with a single number in it, right? 3 columns, each with a single number. So we would call this a 1 by 3 matrix. So since it has a single row, we call it a row matrix. On the other hand, B has how many rows? No, you remember rows run across, so I would think of 7 as a row with a single entry. It's its own row. 6 is a row with its own entry. -5 is a row with its own entry. So there's actually 3 rows, but then there's just one single column. Does everybody see that? Okay. So we call that a column matrix. So this would be a 3 by 1 matrix. And this is how we create all matrix multiplication. We reduce it to a row times a column. So we're going to take A, the vector 2, 3, 4, times B, the matrix going down, 7, 6, -5. So usually what we do is we write it out, 2, 3, 4, there's your matrix A, 7, 6, -5. And the way we define, this is a row matrix times a column matrix, the way it's defined is there's a kind of correspondence, even though those matrices are different orders, there's a kind of correspondence, right? So going across in the first matrix, you have the first entry 2, the second entry 3, the third entry 4. In the first matrix. In the second matrix, you go down, the first entry is 7, the second entry is 6, the third entry is -5. So we just multiply first entry times first entry, second entry times second entry, third entry times third entry, and we add together. So multiply corresponding entries, and what do you get? So this is the work. Now this is the work I will require you to show, because it's really important you know how to do this by hand, so you know how to interpret when you use matrix multiplication to manipulate data. You have to know what is going on by hand, even though you're going to do it by machine, so you can interpret what the output represents. Does that make any sense? You'll see what I mean in just a little bit, if that didn't make sense. So multiply corresponding entry. So you don't have to show me 2 times 7, but you would have to show me the 14. So this first step you don't need to show me. 2 times 7 plus what's the next one? If we write everything out, since it's the first example. So 2 times first entry, add that to second entry times second entry, 3 times 6, add that to what? There you go, third entry times third entry. And then, so this is the step you need to show me, the actual product individually. 14 plus what? 18 plus -20, so -20. I would need to see this. Otherwise, I don't know if you're doing it on the calculator or not. Not that anybody in here would possibly do that, right? Actually, I recommend, if you don't know what to do, I recommend you do that. At least you'll get partial credit, right? But you do need to show, if you want full credit, you need to show me that step. Okay, anyway, what do those add together to be? I think it's going to be 12, isn't it? Yeah. So in your mind, the easy way to do that is to go the 18 minus 20 first, -2, right? Plus 14. Okay? Now let's analyze a couple of things here. The reason why there was that correspondence in the first place that we talked about, between first entries, second entries, third entries, is due to the order. This was a 1 by 3, and A was a 1 by 3, and B was a 3 by 1. So in order for there to be that correspondence, if you have a row matrix and a column matrix, in order for you to have a correspondence, you have to have 3 columns in the first matrix on the left, A, or the same number of columns in A, the first matrix, assuming A is the first matrix, as rows in B. And so it doesn't matter if it's 3, it could be any number, but as long as they match up and are the same. So the number of columns in A, your row matrix, has to match up with the number of rows in B, your column matrix. That's confusing. So just remember that the inner numbers, when you write down the orders, the inner numbers have to match up. And you have to write down the orders in the order that you're multiplying, because multiplication of matrices does not commute. You can't turn it around like you can with real numbers. And that's the reason for the correspondence. If this had been a different number, for instance, then you wouldn't have a first times a first. Well, you could have a first times a first and a second times a second and perhaps a third times a third. But if this had been 4, there would have been another entry down here. And there wouldn't be anything to multiply it by over here. So not all multiplication of matrices is defined.